Okay, let's begin. So the first step, as always, is we need to set our libraries. And we'll enter the standard library that we always enter, which is 1164.all. Now I know that I will be using a counter. I'll be incrementing and decrementing standard logic, so I will also include my unsigned library, and we are also going to use the mycomps package that we have set up previously. So that should be all the libraries and packages that we need. So we can begin the entity. So entity group A is port. So we need to consider the inputs and outputs that we need for this system. So the obvious inputs are the clock, the reset, and the two switches, where one switch is to select whether we're shifting left or right, so we will call that select, and can't call it select, sorry, selection. And the other switch, which shifts it, we will just call shift in standard logic, single bit standard logic. The outputs are simply just the segment displays. So 7 segment 0, and I'm just going to copy and paste that to save myself time. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So we have 6 outputs for the 6 displays. Now each 7 segment display has 7 segments, quite obviously. So for 7 segments, we need to do 6 down to 0, which is 7. And that should be all we need in our entity. So we can end that. And now we start the architecture. So architecture arc, I just call it arc, you can call it whatever you'd like, of group A, can't call that whatever you want, that has to be the same as the entity, is. So the first signal, we need a signal to store the information of the student number, which in this case is just 87654321, a very generic number. Now we know that we can only display 6 digits on the display at any one time, and I'm going to do a single signal called digits for that, and I'm going to store the entire number that we're displaying on the 6 segments at any one time. So that's 6 hex numbers, and we know that for every hex number we need 4 bits. So 6 times 4, that's 24 bits, which is 23 down to 0. You can do it as a single, each signal has 1 hex value. I'm just doing it this way. We will need signals to pass some outputs to inputs of our components, so we will need a signal that does the 1 kilohertz clock divider. 1 kilohertz, so just clock 1 kilohertz, and we also need a signal to come out of the debouncer, which I will call shift dB. Those are both standard logic. We also will need a count value, a count signal that keeps track of where we are when we're shifting left or right. Now, since we're shifting by 2 bits, so 2 values every time, there are only 4 possible positions we can be in, which means that we can do this count in 2 bits, which is 1 down to 0. Missed the O there, down to 0. And that should be all the signals that we need. So let's do our begin, and let's start our components. So first thing, we need a clock divider. So I'm going to call it clock divide 0, and we're going to do clock divider n. And to set that as a 1 kilohertz, I need to put the integer value as 25,000, because that will count 2,000 times per second, which means that we have 1,000 rising edges and 1,000 falling edges. So that amounts to a 1 kilohertz clock output. Simple. For our port map, we just need to feed in our clock, our reset, and we are getting out our 1 kilohertz clock, which I'm passing to the signal I defined earlier. Next one we need to do is the switch debouncing, which I'm going to call switch debouncer when I spell it correctly. And that is going to be our button debouncer component, which is the one that uses the sampling technique, takes 10 samples and then outputs based on the signal being stable. And we just need to write the port map for that. So the switch that is going in is the shift switch, which is switch 0. Shift switch. We need to give it the 1 kilohertz clock signal. It needs the reset, and it's the shift dB that comes out. So that is the debounce signal that we're taking out to use. And that should be all we need for the button debouncer. So with those two components done, we can start our first process. And now this will be the process that actually controls the count value, decrementing and incrementing. So for the sensitivity list, we will clearly need the reset. We're definitely going to need our shift debounce, and we need our selection as well. 3 things we need in our sensitivity list, and we begin that, and we start it with the reset condition, which is an active low reset. So if reset is low, then we are going to set the count to 2, which is 0, 1. And the reason I'm setting it to 2 is that when my count is at its lowest value, the dashes will be apparent on the right hand side, and when my count is the highest value, the dashes will be at the left side. So having the reset set the count to 2 actually puts the highest values of my student number, my fake student number, at the very left hand, which is supposed to be the default position. So that will be fine. And then we're going to do an else if. We're going to do an else if for the rising edge of our debounce, which is shift dB. Then, so now we have a if statement that's looking for, if our reset's not active, it's high, then if we have the rising edge of a switch, we can do something. And the first thing we're going to do when we have that rising edge is check for the state of the selection, if we're going to go left or right. So if selection equals 0, then now if it's a 0, we are going to be decrementing the counter. We're going to be subtracting from the counter because we want to be shifting to the left. And like I said before, when our counter is its lowest value, those dashes are apparent on the right hand side, which means we've shifted all the way to the left. So before I go ahead and decrement it, I need to do one check, and that is my counter already at its lowest value? And that lowest value is 0. So I'm going to say, is my counter greater than 0? If it is, well, sure, you can take 1 from it. Can't spell anything today. -1. However, if this statement's not true, it means it's at 0, which we don't want to go any further. We don't want to do anything if we're trying to subtract it while it's already at its lowest value. So we simply just end the statement. And then we put an else statement here. So now selection is a 1, which means we're incrementing. Now our highest value is a 3. 0, 1, 2, 3. That's 4 possible positions. So we go, hey, is it less than 3? So if you're not at your maximum value, well then sure, you can add 1. And as with the previous one, if it is at its maximum value, we don't want to do anything. We just want it to sit there. So I can end that entire that selection. I can end the rising edge as well, and I can end the process. And this here is going to be my count control. We'll call it shift control actually. It just basically says what position we're at. So now we're going to start a new process. And this process is only going to be sensitive to count, because all this process is going to do is to write the values based on count. So I'm just going to straight away open a case statement and go case count is, let's start with the lowest value. So when it's equal to 0, digits, which is the signal I defined as what I'm going to store the entire number, when it's 0, we know that the dashes are on the right hand side of the screen, which means we've only got half of our number, which if my number is 87654321, then I know on my segments I'm going to have, and I'm writing the X in front because that's how we write hex numbers, is 4321 and then FF. And the reason I write FF is because in my binary to 7 segment component, I have actually changed the case of F to display a dash instead. So this won't display a F, this will display dash. So that will give me 4321 dash dash. Cool. We do the next case, which is 1. And when we're at 1, this simply is going to shift it. So we no longer have any dashes, we have 654321. Simple. When it's the next case, which is also our default case, it's going to be 876543. And when we have our last case, our highest one, which has the dashes on the left, we will have FF again, dashes, 8765. Oops. And that's simple. We can just end that case. I've covered every single possible case in this, so I do not have to include when others. And process. Simple. And that is just writes to digits. Very simple. Now there's one last step I have to do. I have what I want to write to my segment displays, but I haven't actually included the component yet to write to the segment displays. Got tongue tied there, sorry. Write to the segment displays. So let's start with hex 0. And the component's name is binary to 7 segment. We write the port map. So the port map is simply the input and the output. So this is the far right hand side of the segment displays, which means I want to write the lowest digits of my digits signal. And the way I can do that is I can write the digits signal, and then I can open the brackets and actually address 3 down to 0 specifically. And what this does is this looks at those 4 bits specifically out of all the bits, out of all the 24 bits, it's taking these 4 bits and inputting them. And then we just output it, segment 0. Simple. Now I'm actually just going to save myself some time again, and I'm going to copy paste this to have 6 in total. I'm going to change these to 1, 2, 3, 4, and 5. And here in my digits signals, I am going to change this one to 7 down to 4, because 7 down to 4 is the next 4 bits. Then I'm going to change this one to 11 down to 8, because again that's the next 4. And then 15 down to 12. 19, oops, 19, there it is, down to 16, and finally 23 down to 20. And that will write each one of these individual hex values to a single segment display. And then the final step is that I just need to end my architecture. And basically what that will do is, I do not want to save that. Basically what this will do is this will just control the count here and just make sure it doesn't go too high or too low, and just write a value. Oh, I have an actual error here. So the error is actual port 7 segment 0 of mode in cannot be associated with formal port 7 segment of mode out. So what that means is is that I've made an error here, and it's because I've forgotten to write output here. So if the fact that I didn't declare this output here meant that all of these actually defaulted to input. If you don't declare a direction, it will default it to input. And what it's saying is that you can't actually write an output to an input. That's not valid. So we'll just run that again, hopefully with no more silly mistakes, and it should work. One more error, sorry. I've forgotten to update these, so each one should be written to a individual one, just like that. Yes, I would like to save the file. So the fact that I hadn't written these meant that it was trying to write from every component to the same output, and basically you can't do that. You can't write to the same output from 6 different directions. So now it's compiling correctly. So basically this is the end result, is that all you need is 2 processes, one that controls the counter and one that just writes the values. It's a very simple, straightforward way to approach the standard design. There's no complications to it. It's not difficult to understand. Okay, to do the challenge task, what we need to accomplish is to have flashing dashes. So whenever the dashes appear on the segments, they need to flash at 1 Hertz, rate of 1 Hertz. So the first step that I'm going to do is I'm going to introduce a new clock divider, just to accomplish that 1 Hertz. So for 1 Hertz, I know I need a count of 25 million, and I will make a new signal called clock 1 Hertz. And I'll just chuck it in there with my other signals because it only needs to be a bit as well. So I have a new signal called clock 1 Hertz. Simple. Now, the way I'm going to do this is I'm going to update this process here. For the 2 positions that have the dashes, I'm going to put a statement in there that pretty much says whenever the clock is high, write the dashes as dashes, else write them as nothing, write them as clear. So we're going to need to change this top case and this bottom case just a little bit. So I'll make some room to do so. And the first thing I need to do is I need to change this one. So I'm going to get rid of those dashes, and I'm actually going to say digits 23 down to 0. Not 0, sorry. 23 down to 8. So I'm not including the lowest 2 hex bits because they're where my dashes are in this case. So that displays the student number like normal, and we put an if statement in, and the if statement's going to say if clock 1 Hertz, the signal that I've just declared, equals 1, then, and just before I continue, I've just noticed one mistake. I need to change the name of that, otherwise it will return an error. Now I'll continue. So if clock 1 Hertz is 1, then digits 7 down to 0 is going to be FF, because as I stated earlier, FF is what I've changed to be a dash instead. Else digits 7 down to 0 is going to equal the case that I've actually changed to write it as clear on the display, and in this instance I've actually just changed my E case to be a clear instead. So dashes clear. And so what that means basically is that for half a second it will be dashes and half a second it will be clear, meaning that we have flashing dashes at 1 Hertz. Fairly simple. Now we need to do the same process for the other case that has dashes, which you can see right here. So I'm going to get rid of them, and in this case this number is written at the lowest 4 hex bits, so the dashes have to occur at the highest 2 hex bits. So in this case the lowest 4 are 15 down to 0. So we're writing our number to 15 down to 0. And we need to start a new if statement again. And again, if clock 1 hertz is equal to 1, then, oops, then digits. Now we need the highest 2 hex bits this time, which is 23 down to 16. They become my dashes. Otherwise, they are going to be my clear spots, which I have as E. And I just wanted to put clear there. And I just end if. And that's actually the only thing I need to change in that case statement, is that for these two cases here, I'm just changing it around what I write in the digits, and I'm adding an if statement, which I'm allowed to do. So that's basically all you need to do to have flashing dashes. And if I just compile that, and I'll just make sure that I've got no errors, which we had a couple of errors earlier in the standard design, this should work perfectly. Ah yes, now one thing I've just immediately noticed, I'm going to stop it here because warnings are always important to pay attention to. This is giving me a warning saying that my signal clock 1 hertz is read inside the process statement but isn't in the process statement sensitivity list. Now that is actually a big deal in this case. So what it's saying is that, well, you have clock 1 hertz here, but you have not declared it in here. And that is an issue because that means that when I'm not changing my count but it's trying to flash, it will cause errors. So I'm just going to chuck clock 1 hertz in there as well. And I'll just recompile that. So it's a good habit just to sort of keep an eye on the warnings as they scroll through. Every so often you'll catch something that you immediately recognize to be a problem, something that you know is going to cause an error in the design, even if it doesn't appear as an error in the code. And basically now that's compiled, so there should be no errors there, and that's very simply how you do the challenge design. All you need to do is just change when it's writing a dash and just add it when it's to write a clear. Half the time it's not writing a dash. So, onto the champion task. Now, the champion task is actually easier than a lot of people realize, and the first thing you need to keep in mind when doing this task is that for the DE0 board that we use, the buttons are hardware debounced. So each individual button has an RC circuit connected to it that discharges slow enough that you can't actually see the bouncing of the button. So keeping that in mind, the first thing I'm going to do is I'm going to get rid of my debouncer that is going to become redundant. And since the 1 kilohertz clock divider was only servicing the debouncer, that has also now become redundant. So I'm just going to get rid of those two straight away. Now, what we'll have to do, obviously, is we're going to have to change our shift signal, what it's connected to. So previously this was connected to our switch 0. It needs to be connected to button 0, key 0, which I have already taken the liberty of doing. So, very simple. Just change it to the appropriate pin. Now, I do not need clock 1 kilohertz anymore, and I don't need shift dB anymore. Now, what I'm going to do is, now with our new connected button, I'm going to declare a new signal called invert button. And the reason I'm declaring this one is because for the buttons on the DE0 are active low. When I press them, I have a 0, and I still want this to do something when I actually press the button, and I still want to be able to use my rising edge. So if I want this to be a rising edge when I press the button, I need to invert that 0 to a 1. Very simple. So all I'm going to do is I'm going to write a line that says invert button is not shift. Very simple. Now I need to update my sensitivity list. Where I've got shift dB, that is now invert button, and more importantly, where I've got the rising edge is invert button. So now all I've got is a connected button to shift. I'm inverting it here, and I'm just chucking it in my sensitivity list and the rising edge. If this button wasn't hardware debounced, The distinction is that I would have kept the component to debounce it exactly as it was, and then just fed the output of that into this inverter here, because it would still work, but I don't actually need that component because it's hardware debounced. So we'll just go ahead and save this, and we will just quickly synthesize it so that we can check that it has no errors. And assuming that it has no syntax errors, then this code is fine. So that's fine. So this will do the job for the button for the champion tasks, which you literally can get extra marks, bonus marks for a couple of minutes worth of coding, if you know how to go about it the right way. Now, instead of doing a whole nother video for Group B, I thought I would just actually edit this code as Group A and Group B's designs were fairly similar. It's just a matter of the rate that they shift and the dashes at the end. So, just to show the fact they're on Group B, I'm just going to change it to Group B. Completely unnecessary. I'm just going to do it. Okay. And I'm going to file save as Group B. And then I've still got Group A here. Cool. So Group B. And since I've changed the entity names, I'm going to need to update it here to Group B. Cool. Now, the only difference between Group A and Group B was that the Group B had to shift by one spot every time, while Group A was 2, and Group B only needed to show 1 dash on the end instead of 2. So, very simple. The difference is that I just need to change this statement here. I'm not even going to change my counter. That works for both of them. Just my statement here, and update this, because if I want to shift by 1 and have a dash each side, there's actually 5 positions in total that I need to show. So now I'm going to need to change this to 2 down to 0 to show 5 in total. Now, let's come back to our case, and I'm just going to separate this out a little bit as I work on it, just so we can see it a little clearer. For our first one, now, as we discussed previously, we want a dash on the end of it. However, we only want 1 dash now, so we know that this needs to be changed to 3 down to 0 to be only the last one. And I can do 23 down to 4 now, and add a 5. So now all of a sudden I've got 5, 4, 3, 2, 1, and 1 dash. Really easy swap. If I am 1, I've moved over 1. That one is still actually correct, I believe. Yes, it's still correct. The next one needs to be 7, 6, 5, 4, 3, 2 to move over by 1 again. The next one, now I'm actually going to move this down and put when 1, 0, 0, and I will actually add a 0 in front of these, because now I've made it an extra digit, an extra bit longer, I mean. So, we'll shift 1 again. We need to have X 87654. I believe that's enough. 1, 2, no, 3. I missed 1. And then for this case, we need to do the same as we did for the first one. I can change this now to be, I believe it's going to be 19. 19 down to 0. And add a 4 in there. And this can be 20 here, 20 here, there, and there. And one other thing to note is that now I've got uncompleted cases, I need to put a when others here, just so it can consider the other cases. I'm not going to put it in anything in it, because I don't need to. I simply need to just have it there. Now, one other thing, I actually lied before. I said we wouldn't change this. I lied, because we need to change that to a 4. We have 1 extra step that we need to be able to do. So 0, 1, 2, 3, 4. 4 is our highest value now, not 3. So I need to make sure I have a 4. I also need to double check that I'm happy with the starting position, which would be for 2 now. It would be here, which is the middle position, which I believe was correct. I actually do not have the assignment in front of me. If it's not correct, all you would need to do is change this count to be whatever it was, and I need to update this count so it's actually 3 bits. That should be everything you need to do Group B, so let's compile that. We'll let that run, and it will tell me the mistake that I've most likely made. Okay, we have a warning here, and as I was discussing earlier, it's always good to check warnings. So, it's saying I have unsafe behavior now for latch digits and all of them. Now, this warning here is most likely associated with the use of when others here that doesn't actually default to a value. In this instance, it's not a problem. However, this is always one to keep in mind, because this generally just suggests that you can have an unstable signal, something that may not write correctly. In this case, it should be fine. So overall, that is how you do B. That's just a distinction from B to A. The buttons are still the same, the flashing is still the same, just the rate that we count. And hopefully this overall guide has helped students understand perhaps where they went wrong with their practical tests, or better understand a better way to do it. In the end, this is just one of the ways that myself and Ty would do it. So hopefully it's been helpful.